Hello, I'm Seema and welcome to part 26 of the chapter Hydrocarbons. We were doing the chemical properties of alkenes and we started the third property, which is the addition of hydrogen halides to alkenes. And in the previous video, I explained the addition of hydrogen halides where I told you that hydrogen halides like hydrogen chloride, hydrogen bromide and hydrogen iodide are added to alkenes, and the addition is an electrophilic addition, and we did the mechanism also of the addition, and the addition takes place according to Markovnikov's rule. According to Markovnikov's rule, the negative part of the addendum, that is, in each of these molecules, the negative part is the halogen. Hydrogen is more electropositive, so it is the positive part of the addendum, and iodine is the negative. Iodine, bromine and chlorine are the negative parts of the addendum. So whichever is the negative part of the addendum, that is like bromine, we did reactions with bromine, that negative part adds to that carbon of the alkene which has lesser number of hydrogen atoms. So the bromine would add here, and the hydrogen of HBr, the hydrogen would add to the carbon which already has more hydrogen atoms, and the bromine would add here. Therefore, the main product that you would get would not be one bromopropane. Since bromine would add to the second carbon, the main product or the major product that you obtain is 2-bromopropane. Moving ahead with our discussion about the addition of hydrogen halides, if we have a peroxide present in the solution, the addition does not take place according to Markovnikov rule. So, in this video, I'm going to talk about the anti-Markovnikov addition, right? So, anti-Markovnikov addition takes place in the presence of a peroxide. Therefore, it is also known as peroxide effect. And since it was discovered by two scientists, that is M.S. Karash and F.R. Mayo in 1933 at the University of Chicago, they found that in the presence of a peroxide, the addition of the hydrogen halide, and not all hydrogen halides, just hydrogen bromide. So the anti-Markovnikov addition takes place only in the case of hydrogen bromide, not hydrogen iodide, not hydrogen chloride. So this addition takes place, the addition of hydrogen bromide to alkenes takes place against the Markovnikov rule, which means that the negative part of the addendum will not add to the carbon which has lesser number of hydrogens, but will add to that carbon which has larger number of hydrogens. So 1-bromopropane will be your main or the major product. So let us now read this. Anti-Markovnikov addition or peroxide effect or Karash effect. In the presence of a peroxide like benzoyl peroxide, addition of hydrogen bromide only. Remember, this is a very important thing to remember, that this takes the anti-Markovnikov addition or Karash effect takes place only in the case of hydrogen bromide, not in the case of hydrogen chloride and not in the case of hydrogen iodide. So this, in the presence, the addition of HBr takes place to unsymmetrical alkenes. If you remember, in the case of symmetrical alkenes, you cannot tell, there is no preference between which carbon is the halogen adding to or which carbon is the hydrogen adding to, because both the carbons have the same number of carbon atoms around it, around the double bond. So it doesn't make a difference which one going and adding to. So this addition takes place only in the case of both Markovnikov and anti-Markovnikov additions are only relevant in the case of unsymmetrical alkenes. So it takes this addition of hydrogen bromide takes place to unsymmetrical alkenes takes place contrary to the Markovnikov rule, which means against Markovnikov rule. M.S. Karash and F.R. Mayo were the two scientists in 1933 at the University of Chicago. They found this effect, and therefore it is also known after the name of one of these scientists, that is Karash. So it's called Karash effect. So this is propene. And propene, you are adding HBr to propene in the presence of peroxide. In the examination, you may be given the addition of HBr to an unsymmetrical alkene Now what you have to focus on here would be, is the alkene unsymmetrical? Then if it is unsymmetrical, the addition will either take place by Markovnikov rule or it will take place by Anti-Markovnikov rule. If a peroxide is present, then you will have to show the addition to be an Anti-Markovnikov addition. And if the peroxide is not present, then it would be a Markovnikov addition. Another difference between the Markovnikov addition and the Anti-Markovnikov addition is that Markovnikov addition, if you remember, was an electrophilic addition. Anti-Markovnikov addition does not take place by electrophilic addition. The mechanism of reaction is different. So this is a free radical mechanism. It's a free radical addition. Therefore, the mechanism is different, and that's the reason why you get a different product. So what is the mechanism? But before we come to the mechanism of this reaction, let us see that the bond enthalpies of hydrogen chloride, hydrogen bromide and hydrogen iodide are given here. The bond enthalpies of hydrogen chloride, hydrogen bromide and hydrogen iodide are 430.5 kilojoules per mole for hydrogen chloride, 363.8 kilojoules per mole for hydrogen bromide, and 296.8 kilojoules per mole for hydrogen iodide. Now, as I told you that this reaction, the peroxide effect, takes place by free radical mechanism. Just as when we were doing the electrophilic addition or any electrophilic reaction, the first step in that reaction is the generation of that electrophile. Similarly, when a free radical a reaction is proceeding by the free radical mechanism, the first step would be formation of the free radical. So how is a free radical formed? How is an electrophile formed? If HBr breaks in such a way that Br, being more electronegative, takes the electron of the bond, it becomes Br negative and hydrogen becomes H positive. So an unsymmetrical cleavage occurs. Cleavage of the bond, and you get ions, you get Br negative and you get H positive. So Br negative acts as the electrophile. But if a free radical has to be formed, free radical means that both the particles, the pieces that are formed, they should not be charged, which means that when that bond between hydrogen and bromide, since it takes place only in the case of hydrogen bromide, when that bond breaks, hydrogen should get back its electron and form the hydrogen free radical, and bromine should get back its electron and form the bromine free radical. The cleavage should be homolytic. It cannot be a heterolytic cleavage. In a heterolytic cleavage, you will get ions, but in a homolytic cleavage, you will get free radicals. So the first thing is that for the formation of free radical, all of these should undergo homolytic cleavage. So the question is, why do we see the anti-Markovnikov addition only in the case of HBr and not in the case of HI and HCl? This can be explained on the basis of these bond enthalpies. HCl, you see here, has a very high bond enthalpy. Chlorine is far more electronegative. Therefore, the electronegativity, far more electronegative than bromine and iodine. So, the electronegativity difference between hydrogen and chlorine is larger, so it has more ionic character in it. And that is the reason why the breaking of this bond has a very high energy. So, when hydrogen, this is the most electropositive non-metal, hydrogen, and chlorine is a very electronegative non-metal. So when they break, they would prefer not to break to form free radicals. It would usually always be a heterolytic cleavage. It will not be a homolytic cleavage. So free radicals would not be formed. If free radicals will not be formed, they cannot follow the anti-Markovnikov addition, because anti-Markovnikov addition takes place by free radical mechanism. In the case of hydrogen bromide, the energy is 363.8, which is less than 430, and yes, the electronegativity difference is not so much. There is a possibility of homolytic cleavage, and that is why homolytic cleavage takes place. If a peroxide was not present, homolytic cleavage would not have taken place. The addition would have been electrophilic addition. But in the presence of a peroxide, hydrogen bromide undergoes homolytic cleavage and forms free radicals. If that is the case, then hydrogen iodide should also form free radicals because the electronegativity difference between hydrogen and iodine is even lesser and the bond enthalpy is even lesser than HBr. So this should be the one that should form free radicals most easily, but that does not happen. Or rather, I should say it happens. The free radicals are formed very easily, but the problem is that here the two iodine free radicals that are formed, instead of going to an alkene and causing a cleavage of bond there and then adding there, the two iodine free radicals just combine with each other and form an iodine molecule, which is pretty stable, and there is no free radical available to carry out the addition of the hydrogen halide, that is hydrogen iodide. That is why we do not see the anti-Markovnikov addition in the case of hydrogen iodide or in the case of hydrogen chloride. We see this only in the case of hydrogen bromide. Understood? Now let us understand the mechanism, why this happens, and why just by the free radical mechanism the major product changes. So the peroxide effect, it proceeds via free radical chain mechanism. It's a chain reaction. A chain reaction is one which involves many steps, and every next step is related to the previous step. It is like a chain. So what are the steps? There are 5 steps in this reaction. The first step is that you have benzoyl peroxide, and benzoyl peroxide is the peroxide which is causing the peroxide effect or the Karash effect. So benzoyl peroxide, the molecule is C6H5COO and C6H5COO, both the oxygens are joined together. So the cleavage takes place here between the two oxygens of the peroxide. Any molecule which has two oxygens attached like this is known as a peroxide. So this peroxide, when it breaks here, it results in the formation of two benzoyl peroxide. It will form 2 free radicals, and the free radicals will be C6H5COO, and since this bond broke, 1 electron comes here and 1 electron comes to this oxygen. So this is also C6H5COO with 1 dot. And of course oxygen has 6 electrons in its outermost shell, and therefore 1, 2, 3, 4, 5, it has here 5, 6 here, and the 6th electron is a 5 is involved in this bonding, and the 6th electron is here. So you get 2 benzoyl free radicals. But this is very unstable, the free radical. So what happens? It tries to become smaller. The carbon dioxide would rather stay as CO2, and therefore the carbon dioxides, the carbon and the 2 oxygens, they leave. And again, this is also a homolytic cleavage. The carbon dioxide leaves, and now the free radical that becomes is C6H5. C6H5 free radicals, there are 2 of these, and the 2 carbon dioxides from both the free radicals, 2 carbon dioxide molecules are removed. Once the free radical, that is C6H5, is formed, we come to the second step. This free radical causes the homolytic cleavage of hydrogen bromide. So the chain has started. The chain reaction has started. First step was the formation of the free radical. The free radical that was formed was C6H5. This free radical causes the homolytic cleavage of HBr, and so when it causes the homolytic cleavage of HBr, H gets its electron, Br gets its electron. Hydrogen joins this hydrogen with its electron and C6H5 with a separate that is a free electron. Both of them bond together to form C6H6, that is benzene, and bromine free radical is released. This bromine free radical then attacks the alkene molecule in the next step. So in the next step, what happens? The bromine free radical, which was generated in the second step, attacks the alkene and causes the homolysis or the homolytic cleavage of the pi bond. Again, homolytic cleavage would mean that both the carbons will get back their electrons, and bromine will come and add either to this carbon or to this carbon. The bromine free radical, bromine has 1 free electron and both the carbons after the homolytic cleavage have got one free electron. So bromine has a choice. It can either come and join this carbon or it can come and join this carbon. If bromine comes and joins this carbon, the free radical that is formed, where is the site of the free radical? The free radical site is the carbon which has the dangling electron, the free electron. So this is a primary free radical. Why primary? Because the free radical is this single dot. The single dot is on a carbon which is bound only to one other carbon. So if the bromine free radical adds to the second carbon, then a primary free radical is formed. But if the bromine free radical adds to the last or the first carbon, here the terminal carbon, then a secondary free radical is formed. So this is 1 degree, this is 2 degree. Now, if you remember, I told you that more balanced a structure is, the more stable it is. So a free radical or any reaction center which is on the end, that would not be very stable. So a secondary free radical will be more stable than a primary free radical. And you know, in the when we did the Markovnikov addition, there was the formation of carbocation. And we spoke that carbocation, a secondary carbocation is more stable. In that, the hydrogen had added to the molecule and resulted in the formation of it instead of bromine, and the bromine was still staying away as Br negative. So the hydrogen added and formed a secondary carbocation, and therefore the bromine, when it attacked the secondary carbocation, that formed the more stable product. So in that case, this was the more stable product. But here, since the free radical that is formed, the bromine part, the negative part has already added, and now the hydrogen part will have to add. So this secondary free radical that is formed is more stable. So whatever product this gives will be the major product, and whatever product this less stable free radical gives will be the minor product. So in the next step, we come to this, that if you have B, that is the secondary free radical, if that to that HBr is added, and now the bromine part is already there, the hydrogen will come and add here, homolytic cleavage will take place, and again a bromine free radical is produced here. This bromine free radical will again go and attack the next alkene, and thus the chain reaction starts. And this reaction will continue till either all the product finishes, or two free radicals which were not meant to join together, they join and they block each other, whatever, but that would cause the termination of the chain reaction. Here you can also get the minor product. If instead you had the primary free radical which was less stable, to this you add HBr, this would also lead to homolysis, and the hydrogen will come and add here, result in the formation of 2-bromopropane, and bromine free radical will be formed here also. This free radical will again go and attack the alkene, and the same thing, you know, the free radicals that are formed in the reaction mixture, they will help in continuing the reaction, causing the chain to continue. So this was Kharash effect or peroxide effect. So after this, there is one problem that is given in your textbook. Write IUPAC names of the products obtained by addition reactions of HBr to hex 1-ene in the absence of peroxide and in the presence of peroxide. So to do this, you will have to remember, when in the absence of peroxide, what will be the primary product or the major product, and in the presence of the peroxide, what will be the major product. Give me a moment, let me write it down. Now this is solved example, question 13.2 of your NCERT textbook. You have to write the IUPAC names of the products obtained by addition reaction of HBr to hex 1-ene in the absence of peroxide and in the presence of peroxide. We know for peroxide effect, or for the addition of hydrogen halide, that is HBr, and peroxide effect only takes place in the case of HBr. For that, the alkene should be unsymmetrical. So let us first write the formula and see what hex 1-ene looks like. CH2 double bond CH, CH2, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. This is hex 1A. It is unsymmetrical, don't you see? It's so clear that on the two sides of the carbons, this carbon does not have any other carbon attached to it. But this carbon has, on the other side of the double bond, this carbon has a chain of carbons behind it. So it is an unsymmetrical alkene. So yes, it will show the addition by either by Markovnikov rule or by Anti-Markovnikov addition. In the presence of peroxide, the addition will be Anti-Markovnikov. In the absence of peroxide, the addition will be Markovnikov addition. So that is all that we have to keep in mind. The first is that you are adding HBr to this. HBr is to be added to it. So you'll get in the absence of peroxide. In the absence of peroxide, it will be a Markovnikov addition. And what is Markovnikov addition? That the negative part of the addendum will add to that carbon which has lesser number of hydrogen atoms. So which carbon would that be? The second carbon. So we'll get CH3 because the hydrogen will add to this carbon and the bromine will add to the second carbon. So CBr, CHBr, CH2, 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 CH3. This is in the absence of peroxide, right? The second, and what would the name of this compound be? Because it asks you for the IUPAC name of the product. This would be 2-bromohexane. Okay, and let us now carry out in the presence of peroxide. In the presence of peroxide, again we'll write CH2 double bond CH, CH2, 1, 2, 3, 4, 5, and 6 carbons. Plus HBr. This time it is in the presence of peroxide. For the absence of peroxide, you don't need to write anything. It is understood. If something is present, only then we write it. Okay, so in the presence of peroxide, what would happen? The addition would take place according to Kharash effect or Anti-Markovnikov. Anti-Markovnikov said that the negative part of the addendum will add to that carbon which has lesser number of hydrogens. But against this would be the negative part of the addendum will add to that carbon which has larger number of hydrogens. So you, in this case, you will get CH2Br, CH2, the hydrogen will add here and the bromine will add here, and the rest of the molecule remains the same. CH2, 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 CH3. 1, 2, 3, 4, 5, 6. Yes. So how would you give it the IUPAC name? This would be 1-bromohexane. So those are the IUPAC names of the compounds in the presence of the addition product, in the presence of peroxide, and in the absence of peroxide, and in the presence of peroxide. So with this, I'll wind up this video. If you want to watch other videos of this chapter, please click the link that appears on the top of your video. And if you found it helpful, please give this video a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.